The research that I've chosen to look at is around large-scale additive manufacturing, more specifically, research that has led to enhancements in the quality of manufactured parts. I became aware of this technology through the time that I spend in the University of Warwick's build space. The space is run by members of the Digital and Material Technologies Lab group, so they're often working on interesting additive manufacturing projects alongside industrial partners. Broadly speaking, manufacturing techniques fall into two categories, subtractive and additive. Subtractive manufacturing involves removing material to form a shape, and additive manufacturing involves adding material until a desired shape is reached. Large-scale additive manufacturing is the production of parts on the order of meters using additive techniques. The most common technique is fused filament fabrication, or FFF. The machines that use this technique are commonly referred to as 3D printers. FFF works by heating up plastic and pushing it through a nozzle to lay down a bead. Once the printer has traced out the first layer, it moves up and produces the next until the part is finished. Large-scale printers such as the Big Area Additive Manufacturing System can produce parts up to 27 cubic meters at a rate of 50 kilograms per hour. This allows for the production of parts suitable for use across the automotive and aerospace sectors. One measure of quality is how closely the final part's geometry matches the original design. Parts that closely match are said to have good geometric fidelity. The height of each layer is a large factor in the fidelity of the final part. Larger layer heights will result in worse geometric fidelity and vice versa. However, smaller layer heights result in increased print time. This sets up the trade-off between geometric fidelity and print time. In response to this trade-off, the dual-port nozzle has been developed. One way to control the layer height is through the size of the nozzle, and a dual-port nozzle allows the nozzle size to vary between two fixed sizes by extending or retracting a poppet within the nozzle. This allows the designer to vary the layer height and hence geometric fidelity of the part in different regions. The designer can therefore choose which regions require higher fidelity, such as outside surfaces, and which regions can be printed faster but at the expense of fidelity. Dual-port print can therefore give the impressive geometric fidelity of a small nozzle whilst preserving the speed benefits of a larger nozzle, overcoming the trade-off between geometric fidelity and print time. Another measure of quality is the presence of print artifacts. These are irregularities that are introduced into a print that don't occur in theory but do occur in practice. One such example is start-stop extrusion latency. In theory, plastic extrusion can be started and stopped instantly as required. However, in practice, there's a latency between when extrusion is required and when steady-state extrusion is achieved. This latency also exists at the end of the extrusion. This latency can cause print artifacts at the start of layers, as shown on this part. The layer is supposed to start on the corner, however latency has shifted this position to slightly after the corner. In addition, bulging occurs where the printer has laid down more material than it intended to. To combat this, researchers have added an exhaust valve that allows the extruder to reach steady-state extrusion without extruding any additional material onto the part. This works by starting extrusion slightly early and venting the excess material through the exhaust valve. This has the effect that extrusion can be started and stopped instantly as required and leads to much better results. You can see that the start position of the layer has been moved back to its correct position and the bulging has been greatly reduced. We've discussed how one type of print artifact can be reduced, but there are many other types of artifacts that exist as future research possibilities. One interesting way that I think these may be approached is through the use of cameras, machine learning, and computer vision. I myself am currently part of a research project into using thermal vision cameras that can produce images such as this, where the value of each pixel is the temperature of the object at that pixel, in addition to machine learning techniques to produce computer vision algorithms that can monitor the print and detect any artifacts that may lead to possible failure, and then take actions to avoid those failures. One such artifact is insufficient cooling. In theory, the previous layer should be a mechanically sound platform to build upon. However, in practice, not enough time may have elapsed for the previous layer to sufficiently cool, leading to the layers deforming and ruining the part. In this case, the thermal vision cameras could have identified the area that was about to be printed on, realised that it was not cool, and issue a command to slow the printer down. Another issue that could be solved in this manner is under extrusion. This occurs when the extruder is unable to extrude the quantity of plastic that it is expecting, perhaps due to clogging. In this case, the thermal vision cameras could have identified that no continuous beads of hot plastic were being laid down and alerted the operator to check the nozzle for clogging. If you want to learn more about large-scale additive manufacturing, you can look on the Digital and Material Technologies Lab group site or visit the engineering build space at the University of Warwick. Another good resource for papers on large-scale additive manufacturing is sciencedirect.com.